Have you ever wondered where the universe hides its secrets? Not the small ones like where the wind begins or why the ocean tides pull back at the shore, but the deep, absolute secrets that defy the very logic of existence. We live in a world defined by light. It bounces off the leaves of trees, reflects in the glass of your window, and carries the image of the stars across oceans of emptiness to land gently in your eyes. Light is our messenger. It tells us that things exist. It tells us where we are. But there is a place in the cosmos where the messenger is silenced. A place where the light enters but never returns. A place where the map of reality simply stops and the laws of physics, those sturdy rules that govern falling apples and orbiting planets, begin to unravel into something strange and unknowable. Tonight, we are going to drift toward that edge. We are going to journey to the event horizon of a black hole, the silent boundary where the known universe ends and the great mystery begins. So close your eyes. Let the heaviness of the day settle into the ground. Let your breath find a slow, steady rhythm, like a tide moving in the dark. You are safe here. You are anchored in the gentle gravity of Earth, spinning quietly in the arm of the Milky Way. But in your mind, we are traveling far away, past the moon, past the rings of Saturn, past the glittering curtain of stars that make up our sky, to a point of profound darkness. A darkness so complete that it is not just a shadow, but a rupture in the fabric of space itself. Before we cross that threshold, if you are finding a moment of peace in this journey, a gentle like or a quiet tap on subscribe would mean the world to me. It is a small gesture, barely a ripple in the digital ocean, but I hold it with deep gratitude because every bit of your support keeps this tiny universe of stories alive and reminds me that these quiet explorations still find their way to gentle, curious hearts like yours. Now, let us begin. To understand a black hole, we must first unlearn what we know about emptiness. When you look up at the night sky, you see blackness between the stars. But that blackness is not truly empty. It is filled with dust, with wandering atoms, with the faint hum of cosmic background radiation left over from the birth of time. It is a stage waiting for light to cross it. A black hole is different. It is not a stage, it is a trapdoor. Imagine a star, a massive, burning sun, 10 or 20 times the weight of our own sun, living out its life for millions of years. It fuses hydrogen into helium, burning with a ferocious light, pushing outward against the crushing weight of its own gravity. For eons, it is a perfect balance. The energy pushing out matches the gravity pulling in. But eventually, the fuel runs out. The fire dies. And when the fire stops, the balance is broken. Gravity, patient and eternal, wins. The star collapses. It falls in on itself, shrinking, crushing, condensing. If the star is massive enough, nothing can stop the collapse. Not rock, not metal, not even the resistance of atoms themselves. The entire mass of that giant sun is squeezed into a space smaller than a city, then smaller than a house, then smaller than a single atom. It becomes a singularity, a point of infinite density where space and time are curved infinitely. And around that point, gravity becomes so strong that it creates a prison wall made of geometry. This wall is called the event horizon. The event horizon is not a solid surface. You could not stand on it. If you flew toward it, you would not hit a barrier. It is a mathematical line in space, a point of no return. It is the distance from the center where the escape velocity required to break free exceeds the speed of light. Think about that for a moment. The speed of light is the cosmic speed limit, 186,000 miles per second, or roughly 300,000 kilometers per second. Nothing in the universe can travel faster. If light cannot escape, then nothing can. No radio signal, no heat, no information. Anything that crosses that line is gone from our universe forever. It has fallen out of the story of reality. For decades, this idea was just a mathematical ghost. In 1783, an English clergyman and natural philosopher named John Michell first proposed the idea of dark stars, objects so massive that their gravity would trap their own light. He wrote to the Royal Society, suggesting that if a star were dense enough, all light emitted from such a body would be made to return towards it. It was a brilliant leap of imagination, conjured by a man writing by candlelight with a quill pen, dreaming of a gravity that could swallow a sun. But it wasn't until 1915, when Albert Einstein published his general theory of relativity, that the math caught up with the dream. Einstein showed us that gravity is not a force pulling things like a magnet. It is a curvature. Matter tells space how to curve, and space tells matter how to move. Imagine placing a bowling ball on a soft mattress. The mattress sinks, creating a dimple. If you roll a marble nearby, it curves around the dimple. That is gravity. Now, imagine an object so heavy and so small that the mattress doesn't just dimple, it punctures. It creates a bottomless well. That is a black hole. Interestingly, Einstein himself didn't believe black holes were physically real. He thought they were a mathematical oddity, a quirk of the equations that nature would never actually permit. It took a German physicist named Karl Schwarzschild to find the solution. In 1916, while serving on the front lines of World War I, amidst the noise and chaos of battle, Schwarzschild calculated the exact radius to which a mass must be squeezed to become a black hole. He sent his solution to Einstein just months before he died from an autoimmune disease contracted in the trenches. He wrote, "As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." It is a haunting thought, one of the most profound discoveries in human history. The mathematical proof of the eternal dark was found by a man surrounded by the sounds of war, seeking peace in the abstract beauty of the stars. This radius is now called the Schwarzschild radius. For our sun to become a black hole, it would have to be squeezed into a sphere only about 3 kilometers wide. For the Earth, it would need to be crushed to the size of a marble. If that happened, the gravity at the surface of that marble would be so intense that light passing too close would simply spiral in and vanish. For a century, black holes remained invisible, known only by the way they whipped stars around them or heated up gas until it screamed in X-rays. We could see the shadow they cast, the chaos they caused, but never the thing itself. Until recently. In April 2019, the world stopped to look at a picture that shouldn't exist. The Event Horizon Telescope, a global network of 8 radio telescopes synchronized by atomic clocks to act as a single, Earth-sized eye, released the first ever image of a black hole. It was the supermassive monster at the center of the galaxy Messier 87, located 55 million light-years away. The image showed a glowing, fuzzy orange ring surrounding a circle of absolute darkness. That dark circle was the shadow of the black hole. The orange light was not the hole itself, but the superheated gas and dust swirling around it at nearly the speed of light, trapped in a cosmic drain, called the accretion disk. Seeing that image was a moment of collective awe for humanity. We were looking at a void 6.5 billion times the mass of our sun, a gravity well so deep that it could swallow our entire solar system without a hiccup. And yet, in that picture there was a strange stillness. The fiery ring looked motionless, frozen in the vast distance. It reminded us that the most violent things in the universe, when viewed from far enough away, possess a terrible, quiet beauty. NASA scientists describe the event horizon as the ultimate cliff. Imagine you are in a canoe, paddling on a wide, calm river. The water is smooth, the birds are singing, but ahead, the river flows toward a massive waterfall. As long as you are far upstream, you can paddle against the current. You can turn around. But as you get closer to the edge, the current speeds up. The water becomes stronger than your arms. There is a specific point in the river where the speed of the water flowing over the edge is faster than the speed you can paddle. Once your canoe crosses that invisible line, no matter how hard you paddle, no matter how strong you are going over. In space, space itself is the river. And near a black hole, space is flowing inward, falling toward the singularity faster than light can swim upstream. That is why it is black. Light tries to fly away, but space drags it backward. It is a waterfall of geometry, endless and hungry. But what does it feel like to approach such a place? If you were an astronaut drifting toward a black hole, you wouldn't feel a sudden bump. You wouldn't see a sign saying Event Horizon. The boundary is silent. In fact, if the black hole were massive enough, like the one in M87, the tidal forces at the horizon might be gentle. You could cross the line of no return without even realizing it. You would look back and see the stars, see the universe you came from, but you could never send a message to tell them what you saw. You would be cut off from the causal structure of reality. You would have slipped out of history. This is the first great paradox of the black hole. It is a place that is definitely there, and yet, for the observer outside, it is a place where time seems to stop. This is because of gravitational time dilation. As you get closer to the horizon, gravity pulls not just on your body, but on time itself. To a friend watching you from a safe distance, your movements would slow down. Your wave goodbye would take minutes, then hours, then years. The light coming from your ship would grow redder and dimmer as it struggled to climb out of the gravity well, losing energy with every inch. Eventually, to the outside observer, you would freeze. You would remain there, poised forever at the edge of darkness, a faded ghost of light that never quite falls in. But for you, the traveller, time would pass normally. You would look at your watch, and the second hand would tick at the same steady rhythm. You would cross the horizon in a heartbeat, falling into the unknown. The universe behind you would seem to speed up, as if someone had pressed fast forward on the history of the cosmos. You might see stars born and die in the blink of an eye. You would be falling into the future, carried by a river of space that flows towards the end of time. There is a deep humility in facing the event horizon. It reminds us that our intuition, evolved on this quiet, grassy planet, is not equipped for the grand scales of the universe. We are creatures of the middle ground, not too big, not too small, living in a world of moderate gravity and manageable speeds. But the black hole is a creature of the extremes. It is the limit case. It is where nature takes the dials of physics and turns them all the way to the right until the knobs break off. It challenges us to imagine a color darker than black, to imagine a silence deeper than the absence of sound. It asks us to confront the possibility that there are places where here and now lose their meaning. When the Event Horizon Telescope collaboration unveiled the image of Sagittarius A1, the black hole at the center of our own Milky Way in May 2022, it brought the mystery closer to home. This object is only 26,000 light-years away, practically in our backyard in cosmic terms. It is smaller than M87, about 4 million times the mass of the Sun, and it changes rapidly, flickering and shifting like a candle in the wind. The scientists had to develop new algorithms just to catch a clear picture of it, because it wouldn't sit still. It sits there in the direction of the constellation Sagittarius, hidden behind thick clouds of galactic dust, quietly orchestrating the dance of our galaxy. Every star in the Milky Way, including our own Sun, orbits around this center of gravity. We are all, in a sense, satellites of the void. We are tethered to the dark heart of the galaxy, swinging in a vast, slow circle around a point of infinite density. It is not a menacing presence, it is an anchor. Without that deep gravity, the galaxy might not have formed the way it did. The chaos of the early universe needed a center, a seed of heaviness to gather the gas that would become stars. So, in a strange way, we owe our existence to the darkness. It is the loom upon which the spiral of the Milky Way is woven. As we drift here, contemplating the edge of visibility, we feel a sense of scale that is both terrifying and comforting. Terrifying because it makes us feel small, fragile, fleeting. But comforting because it means the universe is vast enough to hold mysteries that we have yet to solve. It means the story is not over. It means there is more to discover. We are standing on the shore of an ocean we cannot sail, watching the waves of space-time crash against a coastline of absolute shadow. And though we cannot cross that line and return, we can send our minds there. We can use the tools of mathematics, the mirrors of telescopes, and the poetry of imagination to touch the edge of the abyss. The event horizon is the beginning of the black hole's riddle, but it is not the end. Once you cross that line, the rules change even more drastically. The familiar comforts of space and direction vanish. Down becomes a destination in time. The future becomes a point in space. The singularity waits not as a place you can avoid, but as a moment you must experience. It draws you in with the inevitability of next Tuesday. But what happens to the fabric of reality as we fall deeper? What happens when space is twisted so tightly that geometry itself begins to scream? That is where we must go next. We must descend past the horizon into the throat of the gravity well to ask the question that haunts physicists and dreamers alike. What lies at the bottom of the dark? The answer involves a warping of the world so profound that it turns the universe into a hall of mirrors. It involves a curvature that defies the straight lines of our understanding. Take a slow, deep breath. The darkness here is gentle. It is the silence before the answer. The horizon is behind us now. We are drifting inward, and the journey is just beginning. The horizon is behind us now. We have slipped past the guardrails of the universe and entered the quiet, forbidden interior. If you were expecting a sudden crash, a violent jolt, or a thunderous roar, you would be surprised by the stillness. According to Einstein's happiest thought, the equivalence principle, falling freely through space feels exactly like floating. Whether you are drifting in the empty void between galaxies or plummeting toward the center of a supermassive black hole. The sensation is identical. You are weightless. You are calm. The event horizon, that terrifying point of no return, has no physical substance. It is not a wall of fire or a barrier of hard glass. It is a shadow line, a mathematical ghost. You could cross it while reading a book or sipping tea, and you would not feel a thing. There is no signpost to tell you that you have just left the universe of the living. There is no bump in the road, and yet everything has changed. You are now in a region of space-time that is disconnected from the rest of reality. If you were to turn on your spaceship's thrusters and try to fly back the way you came, you would find that there is no back anymore. This is the most profound and unsettling truth about the interior of a black hole. Inside the event horizon, space and time swap roles. In the world we left behind, you have freedom in space. You can move left or right, up or down, forward or backward. You can choose where to go. But you have no freedom in time. You cannot stop the clock. You cannot go back to yesterday. You are dragged relentlessly from the past into the future, second by second, whether you like it or not. Inside a black hole, this logic is inverted. The radial direction, the path toward the center, becomes your time. The singularity, that point of infinite density waiting in the dark, is no longer a place in front of you. It is a moment in your future. Trying to avoid the singularity inside a black hole is as impossible as trying to avoid next Tuesday in the outside world. You can struggle, you can scream, you can fire your engines with all the power of 1,000 suns, but you will only reach the end faster. The geometry of the universe has closed like a fist. All paths, all light rays, all possible futures lead downward. You are not falling through space anymore, you are falling through destiny. And as you fall, the view begins to change in ways that defy human comprehension. Imagine looking back over your shoulder. You might expect to see the black hole swallowing you, but remember, the light from the universe is still falling in after you. As you accelerate, the light from the stars behind you gets compressed. The entire universe, the Milky Way, the distant galaxies, the sun you once knew, begins to shrink into a smaller and smaller circle of light above you. This is caused by relativistic aberration. The faster you move, the more your field of view narrows. The vast, infinite cosmos is compressed into a bright, hard jewel of light, a concentrated window looking back at the world you can never return to. The colors of that light would shift. The starlight falling in with you would be blue shifted, energized by the gravity, turning from soft yellow to blinding blue, then to invisible ultraviolet, and finally to X-rays. You are being bathed in the ghost light of the universe, a final, radiant goodbye from the realm of the known. Below you, there is only darkness, but it is not empty darkness. It is a darkness that is waiting. As we drift deeper, we must talk about the feeling of the fall itself. In a supermassive black hole like the one in an M87 or even our own Sagittarius A1, the event horizon is so far from the center, millions or billions of kilometers out, that the gravity at the threshold is surprisingly gentle. You could survive the crossing. You could float there for hours, exploring the quiet interior, a solitary traveler in a bottle cast into the cosmic ocean. But if you were falling into a smaller, stellar mass black hole, a black hole born from a single dying star, the experience would be vastly different. The gravity would be steeper. The danger would be immediate. This brings us to one of the most vivid and terrifying concepts in astrophysics: tidal forces. We know tides on Earth as the gentle rising and falling of the ocean, caused by the moon pulling slightly harder on the water facing it than on the water on the far side of the Earth. It is a difference in gravity across a distance. Near a black hole, this difference becomes a weapon. Imagine you are falling feet first. The gravity at your feet is closer to the singularity than the gravity at your head. In a stellar mass black hole, the difference in pull over just the length of your body, those few feet between your boots and your helmet, would be millions of times stronger than Earth's gravity. Your feet would be pulled down much harder than your head. At the same time, because all paths are converging toward the center, your sides would be squeezed inward. You would be stretched vertically and crushed horizontally. Stephen Hawking, with his gift for finding the poetry in the grotesque, called this process spaghettification. It is a word that sounds almost silly until you realize what it means physically. It is not just your body that stretches. It is the very fabric of the matter that makes you. The molecules in your blood, the cells in your skin, the atoms in your bones, they are all subject to this relentless differential pull. At first, it would feel like a deep, uncomfortable stretch, like waking up from a long sleep. Then it would become a painful tension, as if invisible weights were hanging from your ankles. Finally, the structural integrity of your body would fail. You would be drawn out into a long, thin stream of plasma, a single thread of matter unspooling into the dark. But remember, we are safe here. We are merely observers protected by the comfort of our imagination. We can pause the spaghettification. We can float in the supermassive void where the tides are gentle, where we have time to think before the end. In this quiet interim between the horizon and the center, the laws of physics begin to behave like hallucinations. If you looked to your side, you might see light rays that have been orbiting the black hole for centuries, trapped in a chaotic dance. You might see images of stars that died long ago, their light caught in the gravity well, circling like leaves in a drain. You are walking through a museum of lost light. This region is a space-time trap. Information enters, but it never leaves. This creates a paradox that keeps physicists awake at night: the information paradox. In quantum mechanics, information, the precise state of every particle, is never supposed to be destroyed. If you burn a book, the information isn't gone. It's scrambled into ash and smoke. In theory, if you could collect every particle of ash and photon of heat, you could reconstruct the book. But a black hole seems to violate this rule. If you throw a book into a black hole, it crosses the horizon and vanishes. If the black hole eventually evaporates, a process we will explore later, where did the information go? Did it disappear from the universe? If so, then our understanding of quantum physics is fundamentally broken. Or is it somehow preserved, written on the surface of the horizon like a hologram? This debate has raged for 40 years, pitting giants like Hawking against Leonard Susskind. It is a battle over the basic nature of reality. Is the universe safe for history? Or can the past be truly erased? As you drift in this silent, dark river, you are floating in the middle of that question. You are the data that might be lost. You are the secret the universe is trying to keep. The deeper you fall, the more the geometry twists. Space acts like a lens, bending light into loops. If you could hover here, which you can't, but let's pretend, You might see the back of your own head. You might see the same star appearing in 10 different places at once, a kaleidoscope of gravity. It is a place of illusions, where what you see is not what is there, but what space allows you to see. And beneath all this visual chaos, there is a rhythmic, drum-like pull. The singularity is calling. It is the drain at the bottom of the bathtub. It is the point where the math divides by zero. In mathematics, dividing by zero is an error. It means undefined. It means the equation has broken. In astrophysics, the singularity is where nature divides by zero. It is a point where density becomes infinite, where curvature becomes infinite, where the laws of physics as we know them simply cease to operate. It is the here be dragons of the cosmic map. Some theories, like loop quantum gravity, suggest that the singularity might not be a point at all, but a tiny compressed ball of space-time, a Planck star, where gravity momentarily becomes repulsive, preventing a total collapse. Others, like string theory, propose a fuzzball, a tangled knot of strings vibrating in higher dimensions. But general relativity, Einstein's sturdy old map, offers no such comfort. It predicts a point of absolute end, a place where space and time are extinguished. As we fall toward it, the silence deepens. The radio static from the universe outside has faded to a red-shifted whisper. The light from the aperture above has dimmed to a pinprick. We are alone with gravity. It is a solitude more absolute than anything a human has ever known. On Earth, we are never truly alone. We are surrounded by air, by microbial life, by the hum of the planet's magnetic field. Here, there is only the geometry of the fall. It is a meditative state, forced upon you by the cosmos. You have no choices left to make. You have no destination to select. You are entirely in the hands of the curvature. There is a strange peace in that surrender. The anxiety of what if is replaced by the certainty of what is. The tidal forces in our supermassive black hole are beginning to rise now. The gentle gradient is steepening. The difference in pull between your head and your feet is growing. The comfort of the fall is giving way to the reality of the crush. We are approaching the inner sanctum. The singularity is near. But before we reach that final point, before we touch the place where physics dies, we must ask, is death the only option? Or is the black hole a doorway? For decades, science fiction has dreamed of wormholes, Einstein-Rosen bridges, tunnels that connect one part of the universe to another, or perhaps one universe to a completely different one. Could the bottom of a black hole be the top of a white hole somewhere else, spewing matter and light into a new creation? The math allows for it, technically. A rotating black hole, a Kerr black hole, has a ring-shaped singularity, not a point. In theory, you could fall through the ring without hitting the singularity. You would pass through a Cauchy horizon, a region where the past is fully determined, but the future is unknown. And then, where would you emerge? Would you find yourself in a mirror universe where time runs backward? Would you be crushed by the instability of the wormhole throat before you even took a breath? We don't know. The interior of a black hole is the ultimate locked room mystery. No one who enters ever comes back to tell the tale. It is the one experiment that can only be performed once by one person, with no peer review. As we prepare to face the singularity in our next chapter, take a moment to feel the gravity of your own room. Feel the solidity of the chair beneath you. That resistance, the chair pushing up against your weight, is the electromagnetic force fighting against gravity. It is the force that keeps you whole. It is the force that keeps the Earth from collapsing. Be grateful for it. Be grateful for the structure of atoms, for the stability of matter, for the fact that you live in a universe where space is flat enough to inhabit. In the black hole, that truce is over. Gravity has won the war. The atoms are surrendering. The light is surrendering. And now we are about to meet the victor. The darkness below is no longer just a void, it is a presence. It is the knot where the threads of the universe are tied off. We are drifting closer, the tides pulling at our imagination, the light fading to a memory. We are ready to ask the final question. What happens when space runs out of space? Let yourself drift in this thought. The universe is vast, but it has pockets of intimacy where the rules are rewritten. You have travelled from the safety of your home to the edge of the event horizon, and now you are floating in the deep interior, a place that exists only in the most extreme equations of our ancestors. You are safe. You are exploring. But the journey is not over. The bottom is waiting. And what we find there might not be an end, but a beginning of something we can barely conceive. The darkness is total now. The silence is absolute. We are falling. We are falling. And we are about to hit the bottom. We have arrived at the bottom of the dark. We have fallen past the event horizon, past the point where light turns back, and past the region where the tidal forces stretch matter into atoms. We are now confronting the thing itself, the singularity. In the language of astrophysics, this is the most disturbing concept in the entire universe. It is not an object, it is not a place, it is a failure. When we say singularity, we are using a polite word for a catastrophe in our understanding of nature. According to Albert Einstein's general theory of relativity, the equations that describe gravity work perfectly everywhere in the cosmos, from the orbit of Mercury to the expansion of distant galaxies, until they reach this specific point. Here, the math does not just get difficult, it explodes. The curvature of space-time becomes infinite, the density of matter becomes infinite, the volume becomes zero. Pause and try to hold that thought in your quiet mind. Infinite density, zero volume. It is a paradox that the human brain is not wired to comprehend. How can something that weighs millions of times more than our sun occupy no space at all? How can a mountain fit inside a pinprick? And yet, the math insists that this is where we are. This is the place where physics dies. The sturdy laws that govern the universe, the rules of cause and effect, of energy and mass, of time and space, all shatter against this impossible point. It is the edge of reality's map marked, "Here be dragons." But the dragons are mathematical infinities that we cannot tame. If you were to reach this point, though you would have long since ceased to be you would find that the future ends here. In the outside world, time stretches forward endlessly. Even after you die, time continues for the mountains, for the stars, for the atoms of your body. But at the singularity, time itself stops. It doesn't freeze. It ceases to exist. There is no after. There is no next. The timeline of your existence runs into a wall of geometry and simply terminates. It is the ultimate period at the end of the ultimate sentence. This finality is so absolute, so terrifyingly precise, that physicists have spent the last 100 years trying to prove that it doesn't exist. They have looked for any way to avoid this conclusion, to smooth out the sharp point of the needle. In 1965, the British physicist Roger Penrose, working with the young Stephen Hawking, proved a set of theorems that closed the door on hope. They used profound mathematics to show that under the conditions of a collapsing star, a singularity is not optional. It is inevitable. Once a trapped surface forms, once gravity becomes strong enough to bend light back on itself, the collapse must continue until it hits zero volume. Gravity is too patient, too strong to be denied. It squeezes space until there is no space left. So, according to the classical laws of Einstein, the singularity is real. It is a puncture in the fabric of the universe, a hole where the logic of existence leaks out. But nature, in its quiet wisdom, rarely deals in infinities. Infinite heat, infinite density, infinite curvature. These are usually signs that our theories are incomplete, not that the universe is broken. This brings us to the great conflict, the silent war at the heart of modern physics. It is the clash between the very big and the very small. On one side, we have general relativity, the theory of gravity, which describes space as a smooth, flexible sheet, like a trampoline curving under a heavy ball. It loves smooth lines and gradual changes. On the other side, we have quantum mechanics, the theory of the subatomic world. It describes a universe that is jittery, pixelated, and uncertain. In the quantum world, nothing is smooth. Energy comes in chunks, or quanta. Particles pop in and out of existence. You can never know the exact position and speed of a particle at the same time. The Heisenberg uncertainty principle forbids it. For almost a century, these two theories have lived in separate houses, governing their own domains. Relativity rules the stars. Quantum mechanics rules the atoms. And they get along fine as long as they never meet. But in the singularity of a black hole, they are forced into the same room. We have a star, a massive object, crushed into a space smaller than an atom, a quantum object. We need a theory of quantum gravity to describe it. We need to marry the smooth sheet to the jittery pixel, and so far, we have failed. When we try to combine the equations, they yield nonsense. They predict probabilities greater than 100%, or energies that are infinite. The math breaks down. This tells us that the singularity might not be a point of infinite density after all. It might be something else, something strange and granular that we haven't discovered yet. Imagine zooming in on a digital photograph. From a distance, the image looks smooth and continuous. But if you zoom in far, enough you see the pixels, you see the grid. Many physicists believe that space-time is the same. If we could zoom in on the singularity down to the Planck scale, a distance of 1.64 times 10 to the 35 meters, far smaller than a proton, we might see that space is not a smooth sheet, but a foam. A chaotic, bubbling froth of geometry where space and time are knotted and twisted. In this view, the star doesn't collapse to a point. It collapses to a Planck star or a fuzzball, a tiny, vibrating knot of strings or loops that is incredibly dense but not infinite. It has a size, and if it has a size, then physics doesn't die. It just changes into a language we haven't learned to speak yet. As we drift here in the darkness, waiting for the answer, we realize that the black hole is protecting its secret. There is a cosmic censorship at play. Because the event horizon hides the singularity from the rest of the universe, we can never look inside to see who is right. The universe has locked the evidence in a safe and thrown away the key. We can calculate, we can dream, we can simulate, but we cannot look. This is the source of a deep, intellectual humility. We are standing before a locked door. And perhaps that is a good thing. Perhaps the mystery is what keeps us moving. If we knew everything, if the universe were fully solved, the journey would be over. The black hole reminds us that we are still children, playing with pebbles on the shore of a vast ocean of ignorance. But there is another twist to this story, one that connects the end of time to the beginning. If you rewind the history of the universe, playing the movie of the cosmos backward, you see galaxies moving closer together. You see the universe getting hotter and denser. You go back 13.8 billion years, past the formation of the first stars, past the first atoms, to the very first moment. And what do you find? A point of infinite density, a singularity. The Big Bang, the birth of everything we know, was a singularity. The universe emerged from the very thing that now destroys it. This suggests a beautiful, cyclical symmetry. The black hole is not just a grave, it is a mirror of our birth. We are made of matter that was once crushed into a singularity, and now, in the hearts of collapsed stars, matter is returning to that state. Ashes to ashes, dust to dust, singularity to singularity. Is it possible that the singularity at the bottom of a black hole is a seed? Some theoretical physicists, like Lee Smolin, have proposed the idea of cosmological natural selection. They suggest that every time a black hole forms, a new universe is born on the other side of the singularity. The incredible compression of matter might trigger a bounce, a new Big Bang that expands out into a separate dimension, invisible to us. In this view, our universe is just one bubble in a grand, frothing multiverse, and every black hole is a mother giving birth to a baby cosmos. It is a poetic thought. It transforms the black hole from a monster of destruction into an engine of creation. It means that the death of a star is not an end, but a transformation. The information, the energy, the essence of what falls in is not lost. It is replanted. But let us return to the quiet reality of our fall. We are hovering near the center, in the realm of the unknown. The silence here is heavy. It is the silence of a library where all the books have been burned, or perhaps a library where the books are written in a script no one can read. The tidal forces are absolute now. The geometry is closed. We are wrapped in the deepest darkness that has ever existed. And yet, even here, there is a connection to you, sitting in your room, breathing slowly. The gravity that holds you to your chair, the gravity that keeps the earth orbiting the sun, is the same force that created this abyss. It is all one fabric. You are touching the black hole, and the black hole is touching you, connected by the invisible threads of space-time that stretch across the billions of light years. You are part of the same geometry. Before we move to the next chapter of this mystery, take a moment to feel the stability of your own world. The floor is solid, the air is breathable, the light from your screen is steady. These are gifts. They are the result of a delicate balance in the laws of physics, a balance that allows atoms to hold hands, stars to shine, and minds to wonder. In the black hole, that balance is gone, but because it is gone there, we can appreciate it here. The darkness defines the light. The chaos defines the calm. We have looked into the eye of the monster, and we have found that it is not looking back with malice, but with indifference. It is simply gravity, doing what gravity does when nothing holds it back. As we prepare to leave the singularity behind, or rather, as we accept that we can never leave it, we must ask what happens to the things that fall in. Not the matter, but the meaning. If I drop a letter into a black hole, A letter containing a secret. Is that secret erased from the universe? This question, the paradox of information, is the battleground where the next great revolution in physics will be fought. It is a question about memory. Does the universe remember what it destroys, or is the cosmos capable of forgetting? We have explored the geometry of the trap, and we have touched the point of no return. Now, we must ask about the ghosts that live in the machine. We must ask if the past can truly be deleted. Drifting in this conceptual void, we find a strange peace. We are floating in the gap between what is known and what is true. The standard model of particle physics and general relativity are the two best maps we have, and both of them stop working here. We are off the map. We are explorers in the truest sense. There are no guidebooks for the center of a black hole. There are only questions. And in the quiet of the night, questions are better than answers. Answers end the conversation. Questions keep it going. Questions are the breath of the mind. The singularity waits. It is the period at the end of the sentence of space-time. But is it the end of the book, or just the end of a chapter? As we float here, suspended in the impossible, we begin to sense that there is more to the story. There is a way out, perhaps not for the body, but for the information, for the soul of the matter. The universe is a miser. It hates to throw anything away. And so, in the next stage of our journey, we will look for the escape hatch. We will look for the subtle glow of Hawking radiation, the faint whisper that suggests black holes are not truly black. We will see how the darkness slowly evaporates, returning its stolen energy to the cosmos in a long, cold exhale. But for now, rest in the mystery. Rest in the knowledge that there are things in this universe that are bigger than our understanding, deeper than our logic, and older than our time. The singularity is the ultimate riddle, a Zen koan written in gravity. It asks, what is the sound of one star collapsing? And the answer is silence, a silence so deep it swallows the question. Let that silence wrap around you like a blanket. You are safe, you are home, you are merely dreaming of the deep. And in that dream, we find the courage to ask the next question. If the black hole eats everything, if it swallows light and stars and time itself, does it live forever? Or do monsters die too? The answer lies not in the crushing gravity of the center, but in the empty cold of the space surrounding it. The answer involves quantum magic and particles that steal energy from the void. It is a story of evaporation, a story of how the biggest things in the universe eventually fade away into nothingness. We're about to watch a black hole die, but that is a story for the next drift. For now, we hang suspended in the eternal moment of the center, the place where physics dies and where wonder is born. We are drifting now into a future so distant that the stars we know today are not even memories. They are ancient history, forgotten dust scattered across a void that has grown too big to measure. We have explored the event horizon, that silent waterfall of space. We have fallen through the interior, past the point of no return. We have touched the singularity, the place where physics shatters into silence. And now, we face a question that challenges the very concept of forever. Do black holes last eternally? For a long time, scientists thought they did. In the classical view of general relativity, a black hole is a perfect trap. It can only grow. It eats gas, it eats stars. It merges with other black holes, getting bigger and darker with every meal. According to this logic, once the universe fades and the stars burn out, the black holes should remain, monuments to gravity, sitting in the cold dark, unchanging and immortal, watching the end of time. But in 1974, a young physicist named Stephen Hawking looked at the black hole through a different lens, the lens of quantum mechanics, and he found a leak in the trap. He discovered that black holes are not truly black. They glow, they radiate, and slowly, over oceans of time that defy human imagination, they evaporate. To understand how a monster can die, we must look at empty space. In our ordinary experience, a vacuum is emptiness. It is nothing. But in quantum mechanics, there is no such thing as nothing. The vacuum of space is alive. It is a roiling, boiling sea of energy fields. Everywhere, in every cubic centimetre of the universe, pairs of virtual particles are constantly popping into existence. A particle and its antiparticle, matter and antimatter, blink into being, borrow a tiny amount of energy from the vacuum, separate for a fleeting instant, and then crash back together, annihilating each other and returning the energy to the void. This dance of creation and destruction happens faster than time can measure. It is a quantum jitter, a sparkle in the fabric of reality that keeps the universe buzzing with potential. Usually this dance is invisible. The partners reunite so quickly that they leave no trace. But the event horizon of a black hole changes the rules. It is a boundary, a sharp edge in space. Imagine a pair of these virtual particles popping into existence right on the edge of the cliff. One particle appears just outside the horizon on the safe side. The other appears just inside, in the danger zone. Before they can snap back together and vanish, gravity intervenes. The inner particle is caught. It falls into the black hole, lost forever. The outer particle, now stranded without a partner, cannot annihilate. It has no one to dance with. It's no longer virtual. It has become real. It turns into a real particle of radiation, a photon, a neutrino, a wisp of energy, and speeds away into the universe. To a distant observer, it looks like the black hole has just emitted a particle. It looks like the black hole is shining. This is Hawking radiation. It is the faint, cold glow of the quantum vacuum breaking against the gravity of the dark. But nature is a strict accountant. You cannot create something from nothing. If that escaping particle carries energy away, that energy must come from somewhere. It comes from the black hole itself. Here is the strange, beautiful twist of the math. The particle that fell in must have negative energy relative to the outside universe to balance the books. When it falls in, it doesn't add to the black hole's mass. It subtracts from it. It is like eating a calorie that makes you hungrier. Every time a pair separates and one escapes, the black hole loses a tiny fraction of its mass. It shrinks. The monster is bleeding. It is a slow death. A death so slow that glacial is too fast a word. For a black hole the mass of our sun, the temperature of this radiation is incredibly low, only about 60 nanokelvins, a tiny fraction of a degree above absolute zero. It is far colder than the empty space around it, which is currently warmed to 2.7 Kelvin by the cosmic microwave background. Because the black hole is colder than space, it actually absorbs more heat than it emits right now. It is still growing, but the universe is expanding. It is cooling. Billions of years from now, the background radiation will fade to almost nothing. The universe will become colder than the black hole, and in that distant, silent future, the flow will reverse. The black hole will begin to give back its energy to the void. The timeline of this evaporation is the deepest vertigo you can experience in physics. A solar mass black hole will take approximately 10^, 67 years to evaporate. That is a 1 followed by 67 zeros. To put that in perspective, the current age of the universe is only about 1.38 times 10 years. If the entire history of our universe from the Big Bang to today were compressed into a single second, the lifetime of a black hole would still be trillions of years longer than the age of the stars. It is a span of time that renders the concept of waiting meaningless. And for the supermassive giants like the one in M87, the time is even longer, something like 10 or 100 years. This number is called a googol. It is a time so vast that if you were to count every atom in the visible universe, you wouldn't even be close to that number. It is effectively eternity. But it is not eternity. It is finite. And that distinction matters. It means that the permanent prisons of the cosmos are not permanent. They are temporary holding cells. As a black hole shrinks, it gets hotter. This is another paradox of their thermodynamics. A large black hole is cold and quiet. But as it loses mass, its event horizon gets smaller. The curvature at the edge gets sharper. The tidal forces get stronger. This makes the quantum process of particle creation more violent. The radiation becomes more intense. The black hole glows brighter. It sheds mass faster. It is a runaway process. For billions of eons, it simmers quietly, invisible in the dark. But in its final moments, when it has shrunk to the size of a mountain, then a rock, then a microbe, it erupts. The slow leak becomes a torrent. The black hole explodes with the force of 1,000,000 nuclear bombs, releasing all its remaining mass in a blinding flash of gamma rays and high-energy particles. It goes out not with a whimper, but with a cosmic scream. And then, silence. The singularity is gone. The horizon is gone. The knot in space-time is untied. The geometry smooths out, leaving only a flat, empty calm. This era of the universe, the time when only black holes remain and slowly evaporate, is known to cosmologists as the black hole era. It will be a time of profound darkness. The stars will have burned out long ago. The galaxies will have drifted apart or dissolved. The only light in the universe will come from these rare, dying embers of gravity. Civilization, if it still exists, would have to huddle around these black holes, warming themselves not by the fires of fusion, but by the subtle glow of quantum mechanics. They would be civilizations of the deep dark, harvesting the last drops of order from a dying cosmos. It is a melancholy image, but also a peaceful one. It suggests that the violence of the universe, the crushing gravity, the devouring singularities, is just a phase. It is a storm that eventually blows itself out. There is a lesson in humility here. We tend to think of black holes as the ultimate victors, the apex predators of the universe. We think of them as things that take and never give. But Hawking radiation teaches us that even they must surrender to the laws of entropy. They must give back what they stole. Every star they swallowed, every planet they crushed, every photon of light they trapped, it all eventually returns to the universe, scrambled and changed, but returned nonetheless. Matter is recycled into energy. Energy is spread out into the void. The universe cleans up its messes. Nothing is allowed to hoard existence forever. But this evaporation leads us to the most troubling puzzle of all, the ghost story of physics that we touched on before. The information paradox. If a black hole evaporates completely, what happens to the information of the things that fell in? Remember, quantum mechanics says information is immortal. It cannot be deleted. But Hawking radiation seems to be random. It is thermal radiation, heat without a memory. If I throw a dictionary into a black hole and the black hole eventually turns into a cloud of random radiation and disappears, where did the definitions go? Did the universe lose its memory? If the answer is yes, then the foundations of physics are cracked. It would mean we cannot predict the past or the future with certainty. It would mean reality is leaky. This possibility terrified physicists. Stephen Hawking originally bet that the information was truly lost. He believed the black hole was a supreme eraser. But over decades of debate, the consensus has shifted. Most physicists now believe the information is somehow preserved, perhaps encoded in the radiation itself in a way we can't yet read, or stored on the boundary of the horizon like a hologram. Imagine the event horizon not as a dark curtain, but as a complex, shimmering surface, a hard drive made of geometry. As matter falls in, its information, its spin, its charge, its quantum state might be imprinted on the surface like a sticker on a suitcase. Then, as the black hole radiates, it might pick up that data and carry it back out into the universe. It would be scrambled like a book that has been shredded and mixed into confetti, but it would still be there. If you could collect every photon of Hawking radiation and run it through a supercomputer the size of a galaxy, you could, in theory, reconstruct the dictionary. You could rebuild the star. You could remember the astronaut. This idea, known as the holographic principle, suggests that our entire three-dimensional reality might be a projection of a two-dimensional code stored on a distant surface. It suggests that the universe is less like a room and more like a screen. We might be shadows dancing on a wall of light. Drifting here, watching the imaginary end of a black hole, we feel a strange kinship with these objects. Like us, they are born from the collapse of something else. Like us, they have a lifetime, however long. And like us, they eventually fade, leaving behind only the energy they shared with the world. The scale is different. A human life is a spark, a black hole's life is an aeon, but the arc is the same. We are both temporary patterns in the energy of the cosmos. There is beauty in that transience. If black holes lasted forever, the universe would end up as a graveyard of eternal traps, a place of permanent loss. But because they die, the universe remains dynamic. It remains aflow. The cycle continues even into the deepest, coldest future. As the last black hole in the universe explodes, a Google years from now, it will mark the final event in history. After that, the universe will enter the dark era, or the heat death. Space will be a sea of photons and neutrinos, cooling toward absolute zero, stretching endlessly. Nothing will happen. There will be no clocks to tick, for there will be no change to measure. Time will lose its arrow. It will be a state of perfect, crystalline symmetry. The silence will be total. But it is not a scary silence. It is the silence of rest, the silence of a song that has been sung completely, from the first explosive note of the Big Bang to the final fading chord of the last Hawking particle. It is a completed masterpiece, but we are not there yet. We are here in the vibrant, noisy, spinning youth of the universe. We are living in the stelliferous era, the age of stars. The black holes are still growing. The night sky is still bright. We have the privilege of being awake when the universe is alive. We have the privilege of looking into the dark and asking, what is that? The black hole is a window into the deep future, a reminder of where everything is going, but also a reminder of how precious this moment is. The heat, the light, the complexity of a thought, the warmth of a hand. These are rare treasures in the timeline of eternity. They are the fleeting dreams of the cosmos before it goes to sleep. Take a slow breath. Feel the warmth of your own body. That heat is defiance. It is a temporary rebellion against the cold equilibrium of the future. You are a little pocket of order in a universe that tends toward chaos. You are a burning star in your own right. And just as the black hole eventually gives its energy back, so do we. We borrow our atoms from the earth, we borrow our energy from the sun, and one day we return it. We are part of the great circulation. The journey into the black hole has shown us the extremes of gravity and time, but it has brought us back to the center of our own experience. We are the witnesses. We are the universe remembering itself before it forgets. And yet, there is one more twist to the black hole story. One more possibility that might cheat death entirely. We talked about evaporation, about the slow fade into nothing. But what if the bottom of the black hole is not a dead end? What if the singularity is not a period, but a comma? Some theories suggest that black holes might be the engines of travel, not through space, but through the multiverse. What if falling in is the only way to get out? What if the black hole is a seed for a white hole? This is the realm of wild speculation, the dreamland of physics, where the math allows for impossible things. It is the perfect place for our next drift. We have watched the black hole die in this universe. Now, let us ask if it can be born in another. The darkness around us is thinning. The heavy pressure of the singularity feels less like a crush and more like a squeeze, a birth pang. The radiation is not just waste. Perhaps it is a message. We are ready to turn the page from destruction to resurrection. We are ready to ask, can we go through? The wormhole waits. The white hole shines. The bridge across reality is opening. Let us drift toward that light, the impossible light at the end of the dark tunnel. In the mirrored halls of mathematics, every door that closes must eventually open. We have spent our journey thus far descending. We have fallen through the quiet terror of the event horizon, drifted through the twisted cathedral of the interior, and touched the silent, crushing point of the singularity. We have even watched over the span of eons as the black hole slowly evaporates into the cold night of the future. But there is a ghost in the equations of Albert Einstein, a phantom possibility that suggests the story does not end in darkness. If the black hole is the mouth of a cosmic beast that swallows matter and light, is there an exit? Does the universe have a reverse gear? In 1935, Einstein and his colleague Nathan Rosen toyed with the geometry of these gravity wells and found something startling. They discovered that the funnel of the black hole might not just pinch off into nothingness. Instead, it might connect to another funnel, an inverted one, opening up somewhere else. This connection is technically called an Einstein-Rosen bridge. Science fiction knows it by a more poetic name, a wormhole. And the exit at the other end, the radiant twin of the black shadow, is called a white hole. Imagine a film of a black hole played backward. In the forward version, things fall in and never come out. In the backward version, things come out and can never fall in. A white hole is a region of space-time where gravity pushes rather than pulls. It is a cosmic geyser. While a black hole is a region of absolute darkness from which nothing escapes, a white hole is a region of absolute light which nothing can enter. If you were to point your spaceship toward a white hole, you would see a blinding brilliance, brighter than 1,000,000 suns, spewing matter and energy into the universe. But no matter how hard you fired your engines, you could never reach the event horizon. The space itself would be flowing outward at the speed of light, pushing you away, protecting its interior from any intrusion. It is the ultimate do not enter sign of the cosmos. For decades, physicists dismissed white holes as mathematical curiosities, perfectly valid on paper, but impossible in the messy reality of our universe. They argued that there is no physical way to form one. A black hole forms from the collapse of a star, a clear physical process. But a white hole would require a movie running in reverse, a star uncollapsing, gathering dust from the universe and spitting it out into a solar shape. It violates the second law of thermodynamics, which says that entropy, or disorder, must always increase. And yet, the math persists. It whispers that the singularity at the bottom of a black hole might not be a dead end, but a throat. When we discussed the ring singularity of a rotating Kerr black hole, the type of black hole that actually exists in our spinning universe, we touched on a loophole. As we learned from the study of cosmic rotation, a spinning black hole drags space-time around with it, creating a vortex. At the center, the singularity is not a point, but a ring of infinite thinness. If you fall towards a non-rotating black hole, you hit the point and die. But if you fall toward a spinning one, the centrifugal force of the rotation fights against the gravity. There are trajectories, specific paths through the chaos, where you could technically miss the singularity. You could fly through the center of the ring. And if you did, where would you go? The equations of general relativity suggest you might pass through the throat of the wormhole and emerge from a white hole in a different region of space, or perhaps a different time, or even a completely different universe. Let yourself float in that possibility for a moment. Imagine the journey. You fall into the black hole, bracing for death. The darkness swallows you. The tidal forces stretch you. But just as the pressure becomes unbearable, you slip through the eye of the needle. Suddenly, the crushing weight reverses. You are no longer falling in. You are being expelled. The darkness creates a blinding flash of white. You are thrown out into a new sky, unfamiliar stars blazing above you, a new galaxy spiraling in the distance. You have cheated death. You have used the monster as a subway tunnel to the stars. This idea has captivated dreamers and scientists alike because it solves the emotional problem of the black hole. It turns a grave into a gate. It suggests that the universe is not a collection of isolated islands, but a vast, interconnected web where space folds over on itself like origami. However, the universe is rarely so obliging. There is a catch, a gotcha hidden in the fine print of the laws of physics. The Einstein-Rosen bridge is incredibly unstable. In a standard black hole, the wormhole pinches shut faster than the speed of light. If you tried to cross it, the tunnel would collapse on top of you before you could reach the other side. You would be crushed not by the singularity, but by the closing of the door. To keep the throat of the wormhole open, to shore up the walls of the tunnel so a spaceship could pass, you would need something that might not exist. Exotic matter. This is matter with negative mass and negative energy density. In our world, everything has positive mass. Gravity pulls. Negative mass would have gravity that pushes. It would act as a scaffold, holding the mouth of the wormhole open against the crushing weight of space-time. We have never seen large chunks of negative mass. We have seen tiny hints of negative energy in the quantum vacuum, the Casimir effect, where two metal plates are pushed together by the pressure of empty space. But constructing a stargate out of it is a feat far beyond our current understanding. So, the white hole remains a mirage. We have never observed one in the sky. Every time astronomers see a burst of high energy, like a gamma-ray burst, they briefly wonder, is that a white hole? But so far, the answer has always been a collapsing star or a colliding neutron star. The universe seems to prefer the black hole, the eater, over the white hole, the giver. But this absence leads to an even deeper question about the nature of time. If the equations allow for white holes, but nature forbids them, it means the universe has a preferred direction. It means time is not just a coordinate, it is an arrow. The black hole is an engine of the future. It turns matter into entropy. A white hole would be an engine of the past, turning entropy into order. The fact that we don't see them is evidence that we are locked in a one-way flow. We are passengers on a train that cannot reverse. Or are we? There is a theory championed by physicists like Carlo Rovelli that suggests white holes are not fiction, but the future of black holes. Remember the Planck star, the tiny compressed core we imagined replacing the singularity. Rovelli suggests that when a black hole finishes evaporating, when it has shrunk down to the size of a proton, quantum gravity takes over. Space rebounds. The collapse halts and bounces back. The black hole instantly, in its own time, turns into a white hole. But because of the extreme time dilation inside the hole, this instant bounce looks like billions of years to us on the outside. In this view, every black hole we see in the sky is a star that is currently collapsing and bouncing back in slow motion. Billions of years from now, when they finish their long wait, they will pop like microscopic bubbles, releasing all the information they swallowed in a gentle shower of information. If this is true, then white holes are all around us, hidden in the hearts of darkness, waiting for their moment to bloom. It would mean that the death of the black hole is not a fade out, but a transformation, a heartbeat that takes an eon to beat. This concept connects us back to the sheer scale of the cosmos. We look at the sky and see static points of light, but the reality is a breathing, pulsing, transforming beast. The black holes are the lungs of the universe, inhaling matter and holding it, compressing it, perhaps refining it before exhaling it back into the void. It recontextualizes our fear. If the black hole is a temporary holding state, a cocoon for matter, then falling in is not the end of existence. It is a pause, a long, dark sleep before a new awakening. It brings a sense of rhythm to the violence. The universe destroys to create, it folds to connect, it hides to reveal. But let's return to the bridge. If a wormhole could be held open, if we could find the exotic matter to prop up the door, the implications would shatter our reality. A wormhole connects 2 points in space, yes. But because space and time are woven together, it also connects 2 points in time. If you move one end of the wormhole at near light speed and bring it back, you create a time machine. You could step into one mouth today and emerge from the other mouth yesterday. This is where the headache of the black hole turns into the nightmare of causality. The universe protects its history fiercely. If you could go back, you could change the past. You could stop the black hole from forming. You could stop yourself from entering. This creates the grandfather paradox, the loop of logic that destroys coherence. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics will always conspire to destroy a time machine before it can be used. Vacuum fluctuations would build up in the loop, creating a feedback screech of energy that would vaporize the wormhole the moment it became a time tunnel. The universe, it seems, refuses to be edited, and yet the dream remains. As you drift here, suspended between the crushing singularity and the theoretical exit, you are caught in the tension between what is possible and what is permitted. The black hole is the limit of our freedom. It is the wall we cannot climb. But the white hole is the window we draw on that wall. It represents our refusal to accept finality. We look at the dark and we say, there must be a light on the other side. It is a deeply human impulse. We are creatures of hope. We are creatures who build bridges. And even if the Einstein-Rosen bridge is a bridge to nowhere, the math that describes it has led us to deeper truths about quantum entanglement and the nature of space itself. In recent years, a new idea has emerged, ER to EPR. This equation, proposed by Juan Maldacena and Leonard Susskind, suggests that wormholes, ER, and quantum entanglement, EPR, are the same thing. Entanglement is the spooky connection between two particles where changing one instantly affects the other, no matter how far apart they are. The theory suggests that these particles are connected by tiny microscopic wormholes threading through the fabric of space-time. If this is true, then space is not an empty stage. It is stitched together by billions upon billions of tiny black hole bridges. You are held together by wormholes. The gravity that keeps your feet on the ground might be the collective pull of these quantum threads. The black hole is just a magnification of the glue that holds reality together. So, we have gone from the monster that eats stars to the thread that weaves the cosmos. The black hole is not an anomaly. It is the archetype. It is the purest expression of the geometry that defines us. As we leave the hypothetical brilliance of the white hole and drift back into the shadows, we carry a new perspective. The darkness is not empty. It is pregnant with possibility. It is a knot that ties the universe to itself. We have explored the bridge through space. We have looked for the exit. But the black hole has one more trick up its sleeve. It doesn't just bend space. It breaks time. And if time is broken, what happens to the clock? What happens to the past? In our next chapter, we will stop moving through space and start moving through the fourth dimension. We will ask if the black hole is a time machine, not just in theory, but in practice. We will look at how gravity slows the ticking of the heart and how a journey to the event horizon is a one-way ticket to the future. The time travel is real. The question is, how far can we go? Rest now, traveller. The white light has faded. The wormhole has closed. But the clock is ticking slower and slower, and the future is rushing to meet us. Part 6. Is the black hole a time machine to the future? Time is not a constant. It is a river that flows at different speeds depending on where you swim. We feel it passing steadily, 1 second per second. But that stability is an illusion caused by the weakness of Earth's gravity. We live in a quiet, stagnant pool at the edge of the river. Near a black hole, the river becomes a rapid. Einstein's relativity tells us that gravity drags time. The stronger the pull, the slower the clock. This is not a mechanical error. It is a fundamental property of the universe. Time dilation. If you were to orbit close to the event horizon of Sagittarius A, just above the point of no return, for every minute that passed for you, hours or days might pass for the people back on Earth. You are not just traveling through space, you are traveling through time. This is not science fiction. We measure this effect every day. The GPS satellites that guide your car orbit the Earth in weaker gravity than we feel on the surface. Their clocks run faster than ours by about 38 microseconds a day. If we didn't correct for this difference, the entire GPS system would fail within hours. We are already accounting for time travel in our daily commute. But a black hole magnifies this effect to a mythological scale. Imagine you are the astronaut we left at the horizon. You decide to hover there, firing your engines to resist the pull, hanging just inches above the darkness. You look out at the universe. What do you see? Because your time is running so slowly compared to the outside, the rest of the universe appears to be running fast. You would see the stars wheeling overhead like streaks of fire. You would see galaxies rotating in seconds. You would see the eons of cosmic history playing out in fast forward. You are watching the future of the universe unfold before your eyes. If you stayed there for a year, according to your ship's calendar, and then flew back to Earth, you might find that thousands of years had passed. Your friends would be long dead. Your civilization might be dust. The language you speak might be forgotten. You would be a relic from the past, a time traveler who has jumped into the future. This is the only form of time travel that physics unequivocally allows. It is a one-way ticket. You can go to tomorrow, but you can never return to yesterday. The black hole is a preservation chamber. It keeps you young while the universe grows old. There is a profound melancholy in this truth. The price of seeing the future is the loss of your present. To touch eternity, you must let go of everyone you love. It is a solitary journey. The gravity that holds the black hole together also separates you from the timeline of humanity. You become an island in time. But what if you went deeper? Inside the horizon, as we discussed, time and space swap roles. The future becomes a direction. Does this mean you could navigate to a specific time? In a rotating Kerr black hole, there are regions deep inside, near the ring singularity, where the dragging of space-time is so violent that time loops back on itself. These are called closed time-like curves. In these loops, the future leads back to the past. If you followed one of these curves, you could, in theory, meet yourself before you left. You could shake your own hand, but here the universe draws a line. These loops are buried deep behind the horizon. They are hidden from the rest of the cosmos. Whatever happens in the time loop stays in the time loop. You cannot come back out to Earth and kill your grandfather. You are trapped in a private paradox, a bubble of circular time cut off from history. It is as if the black hole says, you can play with time, but only in the dark. The censorship holds. The timeline remains safe. As we ponder this, we realize that gravity is the architect of our experience of now. We share a moment with someone because we share a gravitational field. We are synchronized by the Earth. But the universe has no single now. There is no cosmic clock on the wall. Every star, every planet, every black hole has its own time, its own rhythm. The cosmos is a symphony of different tempos, all playing at once. The black hole is the bass note, the slow, deep vibration that anchors the melody. It reminds us that time is precious not because it is absolute, but because it is relative. It is a relationship. We are drifting away from the time loops now, pulling back from the brink of the paradox. We have seen the white hole, the wormhole, and the time machine. We have seen how the black hole bends the rules of reality, but we have not yet asked how these monsters shape the universe we see today. They are not just oddities, they are anchors. Without them, we might not be here. In the next chapter, we will leave the theoretical world of the interior and return to the visible universe. We will look at the supermassive black holes that sit in the hearts of galaxies like spiders in the center of webs. We will ask, did the black hole create the galaxy? Or did the galaxy create the black hole? The answer is a dance of creation and destruction that has lasted for 13 billion years. The darkness is vast, but it is not empty. It is full of structure. It is full of history. And we are about to see how the invisible sculptors have shaped the night sky. The journey continues upward and outward to the giants that hold the stars. When you look up at the Milky Way, that river of silver light stretching across the dark, you are seeing a city of stars. Billions of suns drifting in a vast, silent spiral, holding their planets like lanterns against the cold. It looks peaceful. It looks stable. But if you could strip away the starlight and look only at gravity, you would see that the entire galaxy is spinning around a drain. We are orbiting a monster. At the exact center of our galaxy, hidden behind thick curtains of dust in the constellation Sagittarius, sits Sagittarius A. It is a supermassive black hole, 4 million times the mass of our Sun, compressed into a space no larger than the orbit of Mercury. It is the anchor of our cosmic home. And we are not alone in this arrangement. Almost every massive galaxy in the universe, from the neighborly Andromeda to the distant giants seen by the Hubble Space Telescope, possesses a dark heart. These are not the small, stellar mass black holes formed from dying stars. These are titans. Some, like the one in the galaxy TON 618, are 66 billion times the mass of the Sun. They are so large that light would take weeks to cross their event horizons. For a long time, astronomers thought these giants were just passive residents, accidents of gravity that grew fat over time, sitting quietly in the basement of the galaxy. But we now know that is not true. They are not just residents. They are the architects. The relationship between a galaxy and its black hole is one of the deepest mysteries in cosmology. It is a question of scale that defies logic. The black hole is tiny compared to the galaxy, like a grapeseed in the middle of a football stadium. And yet, the two are intimately connected. In the year 2000, astronomers discovered a strange correlation known as the M-sigma relation. They found that the mass of the central black hole is almost perfectly tied to the speed of the stars in the galaxy's outer bulge. The bigger the black hole, the faster the stars move, even those that are thousands of light years away. It is as if the grapeseed is somehow controlling the speed of the fans in the stadium seats. How can something so small dictate the structure of something so vast? It suggests that they grew together, that the galaxy and the black hole are not separate things but two parts of a single organism, evolving in lockstep over billions of years. This leads to the classic chicken or egg problem of the cosmos. Which came first? Did the galaxy form a cloud of gas that slowly collapsed to create a black hole? Or did a primordial black hole form in the silence of the early universe, and its gravity pull the gas in to build the galaxy around it? Recent discoveries by the James Webb Space Telescope have deepened this puzzle. JWST has peered back to the dawn of time, just a few 100 million years after the Big Bang, and found black holes that are far too big to exist. According to our standard models, black holes should grow slowly, feeding on gas and merging over eons. But these ancient giants are already fully grown, sitting in baby galaxies that are barely formed. It is like walking into a nursery and finding a fully grown oak tree planting acorns. This suggests that the black holes might have been the seeds. They might have been the anchors that allowed the first galaxies to coalesce out of the primordial fog. In this view, we owe our existence to the dark. Without the stabilizing grip of that central gravity, the Milky Way might never have formed its spiral arms. The sun might never have ignited. The Earth might never have been born. We are here because the void held us together. But the black hole is not just a passive anchor, it is also a regulator, a governor of life. A galaxy is a star-making machine. Gas clouds collapse, stars ignite, they live, they die. If this process happened unchecked, a galaxy would burn through all its fuel in a glorious, short-lived burst. It would become a starburst galaxy, shining brilliantly for a brief epoch and then burning out, leaving nothing but cinders. The black hole prevents this. It acts as a thermostat. When a black hole feeds, it doesn't just swallow, it spills. As gas spirals into the accretion disk, it rubs against itself, generating friction and magnetic fields that heat the material to billions of degrees. This process turns the black hole into a quasar, the brightest object in the universe. A single quasar can outshine 1 trillion stars. It fires jets of particles near the speed of light, shooting out from the poles like cosmic lighthouses, piercing through the galaxy and into intergalactic space. These jets act like a wind. They push against the gas in the galaxy, blowing it away, heating it up, preventing it from cooling down enough to form new stars. It is a violent, beautiful feedback loop. The galaxy feeds the black hole. The black hole wakes up, ignites, and pushes the food away. The star formation stops. The galaxy rests. Then, millions of years later, the gas cools and falls back in, and the cycle begins again. This breathing of the black hole regulates the life of the galaxy. It ensures that the fuel is used slowly over billions of years, allowing stars like our sun to be born in a quiet, stable era. In a poetic sense, the black hole kills the galaxy a little bit to save it from dying too young. It imposes moderation on the chaos of creation. So, when you look at the peaceful night sky, you are looking at a stillness that was purchased with violence. You are seeing a balance maintained by the monster in the middle. There is a profound humility in realizing that our quiet corner of the universe is governed by such forces. We tend to think of life as fragile, something that exists in spite of the cosmos. But the physics of black holes suggests that life is a beneficiary of the cosmos's most extreme structures. We are sheltered by the storm. We are orbiting a drain, yes, but it is a drain that keeps the water flowing at the right speed. And this relationship is not static, it is evolving. Right now, Sagittarius Aeor is quiet. It is on a diet, consuming only wisps of gas and the occasional asteroid. It is a sleeping dragon. But it wasn't always so. Astronomers see Fermi bubbles, giant lobes of gamma-ray radiation extending above and below the Milky Way, which are the fossilized remnants of a massive eruption that happened millions of years ago. Our black hole was once a quasar, and it will be again. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. It will be a cosmic ballet of slow-motion destruction. The two galaxies will pass through each other, their stars dancing past without colliding, but their gas clouds smashing together. Gravity will funnel oceans of fresh fuel into the centers. The sleeping giants will wake up. The black holes of both galaxies will ignite, shining as quasars, illuminating the merger with the light of a dying sun. Eventually, the two black holes will find each other. They will spiral inward, drawn by the inexorable tug of gravity, until they merge into a single, even more massive singularity. The universe is a story of mergers. Small things come together to make big things. Big things come together to make giant things. And at the end of the road, the black holes are waiting to collect it all. This thought might seem terrifying, the idea of an inevitable descent into the dark. But there is another way to see it. It is a story of unity. Gravity is the force of attraction. It is the universe trying to return to oneness. From the scattered dust of the Big Bang, gravity builds stars. From the stars, it builds galaxies. From the galaxies, it builds clusters. And in the hearts of those clusters, the black holes act as the ultimate binders. They are the knots that hold the tapestry tight. Without them, the universe would be a loose, drifting mist. With them, it is a structure. It is a home. As we drift near the center of our own galaxy, observing the invisible influence of Sagittarius A's, we feel a sense of gratitude for the architecture of the night. The black hole is not an enemy. It is the keel of the ship. It keeps us steady in the ocean of space-time, and it reminds us that visibility is not the only measure of importance. The most powerful things in the universe are often the ones we cannot see. They are the silent forces, the hidden masses, the quiet pulls that guide us without our consent. But what happens when two of these architects clash? What happens when the immovable object meets the unstoppable force? When two black holes merge, they don't just create a bigger hole. They break the silence of the universe. They shake the very fabric of space-time, sending out ripples that stretch and squeeze the geometry of reality itself. These ripples are called gravitational waves. They are the sound of gravity. For most of human history, we have been deaf to the universe. We have looked with our eyes using telescopes to catch light, but we have never heard the dark, until now. In our next chapter, we will open our ears. We will listen to the song of the black holes. We will learn how a ripple in space, smaller than a proton, travelled for 1 billion years to ring a bell on Earth, confirming the last and most elusive prediction of Einstein. We are done watching the architects build. Now, we will hear them sing. The universe is about to get very loud. Part 8. The Sound of Gravity. For 13.8 billion years, the universe was a silent movie. We watched the stars explode, the galaxies spin, and the comets trail their tails of dust, but we watched it all in the spectrum of light. Light is a wave of electromagnetism. It can be blocked, it can be scattered, it can be absorbed by dust. It shows us the surface of things, the glowing skin of the star, the hot gas of the nebula. But gravity is different. Gravity is not a wave travelling through space. It is a waving of space. It passes through matter as if it weren't there. It carries the story of the bulk, the mass, the deep movement of the cosmos. And when massive objects move, they make noise. Albert Einstein predicted this in 1916. His equations showed that if you take two massive objects like black holes or neutron stars and spin them around each other, They should churn up the space-time around them like a paddle in a pond. Ripples should spread out from the disturbance, traveling at the speed of light, carrying energy away from the system. As the black holes lose energy, they spiral closer. They spin faster. The ripples get stronger. The frequency goes up. It becomes a chirp, a rising tone that ends in the sudden silence of the merger. Einstein thought these waves would be too weak to ever detect. He thought the song was too quiet for human ears. For 100 years he was right. The universe hummed, and we went about our business, deaf to the vibration of the ground beneath us. But on September 14th, 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, felt a shudder. It wasn't an earthquake. It wasn't a truck driving by. It was a ripple in space-time that had traveled for 1.3 billion years to reach us. It came from a place in the southern sky where two black holes, one 29 times the mass of the Sun and the other 36 times the mass of the Sun, had finally collided. In the fraction of a second before they merged, they were spinning around each other hundreds of times per second, moving at half the speed of light. The power released in that final instant was 50 times greater than the light of all the stars in the visible universe combined. It was the most powerful event humans have ever detected, and yet it was invisible. No telescope saw a flash. No camera caught a glow. The event was pure darkness. But it was loud in gravity. When the wave passed through Earth, it stretched and squeezed the planet by a fraction of the width of a proton. The LIGO detectors, two giant L-shaped tunnels in Washington and Louisiana, measured this tiny distortion using lasers. They caught the chirp. It was a sound from the deep past, a thud on the door of reality. It changed everything. Suddenly, we were not just viewers. We were listeners. We had a new sense. We could hear the dark. Since then, we have detected dozens of these mergers. We have heard black holes crashing into neutron stars. We have heard the ringing of the new black hole as it settles down after the collision, a wobble of space-time that reveals its mass and spin. We are mapping the graveyard of the stars, finding invisible monsters that we never knew existed. This creates a profound shift in our connection to the cosmos. Before, space felt empty, a vacuum separating the stars. Now, we know it is a medium. It is a fabric that vibrates. Right now, as you sit there, gravitational waves from distant collisions are passing through your body. They are stretching you and squeezing you, ever so slightly, connecting you to the violent deaths of stars and galaxies far away. You are vibrating with the universe. You are part of the drumhead. The silence of the room you are in is an illusion. Beneath the range of your hearing, the air is filled with the symphony of gravity. And this song is not just noise, it is history. These waves travel unimpeded. They carry the pure, uncorrupted signature of the event that created them. Light gets tired, it gets redshifted, absorbed, scattered. Gravity remembers. Someday, we hope to build detectors sensitive enough to hear the primordial gravitational waves, the ringing of the Big Bang itself. We might be able to hear the sound of the universe being born. We might be able to listen to the moment of inflation when the cosmos expanded faster than light, setting the drumhead vibrating for all eternity. There is something deeply meditative about this. We usually associate knowledge with seeing. I see, we say, when we understand. But hearing is a more intimate sense. It requires silence. It requires patience. You cannot look away from a sound. It enters you. Listening to the universe requires us to quiet our own noise. It requires us to build machines that are so still, so isolated from the vibrations of the human world, that they can feel the tremble of the stars. It is an act of technological contemplation. We have built cathedral-like ears to catch the whispers of the gods. The sound of a black hole merger is fleeting, a whoop that lasts less than a second. But in that second, two distinct things become one. Two event horizons, two separate regions of no return, touch and merge. There is a moment just before the end when the two holes are connected by a neck of darkness, a bridge that widens until the two spheres become a single, distorted peanut shape, which then instantly snaps into a perfect sphere. It is the geometry of unity. It is the ultimate embrace. In a universe that is expanding, drifting apart, cooling down, the black hole merger is an act of gathering. It is gravity fighting back against the dark energy that pushes us apart. As we drift in the afterglow of this thought, we realize that the universe is not a static painting. It is a song. It has rhythm. It has crescendos. It has periods of quiet. And we are just learning to read the sheet music. We have heard the violins of the black holes. Now we are waiting for the drums of the Big Bang. The journey into the black hole has taken us from the visual, the shadow, the ring of light, to the auditory, the chirp, the ring of space. We are engaging with the cosmos with all our senses, even the ones we had to invent. But there is one more barrier to cross. We have looked at the black hole from the outside, and we have imagined the inside. We have heard its crash, but we have not asked the question that touches the very nature of our own minds. If the universe is a hologram, if information is stored on the horizon, if black holes are the hard drives of reality, are we inside one right now? There is a theory, a whisper in the halls of cosmology, that our entire universe, the billions of galaxies, the expansion, the dark energy, might be the interior of a black hole in a much larger, older universe. It is the ultimate nesting doll. It would explain why the singularity of the Big Bang looks so much like the singularity of a black hole. It would explain why we can't see the edge. We might be living in the deep interior of a giant's eye. In our next chapter, we will turn the camera around. We will stop looking at the black hole as an object out there and ask if it is the container in here. We will explore the idea of the black hole universe. Are we the dream of a falling star? The journey is about to get very big and very close to home. The most frightening thing about a prison is not the walls, but the possibility that you might not know you are inside one. We look out at the universe and we see vastness. We see a frontier that seems to stretch forever, an open ocean of galaxies expanding into the dark. We feel free. We feel unconfined. But geometry is a master of disguise. As we have traveled through the chapters of this cosmic story, we have learned that black holes are not just holes, they are worlds. They have horizons, they have interiors, they have a specific mathematical architecture. And when physicists look at the architecture of our own universe, the way it expands, the way it curves, the amount of mass it contains, they notice a haunting similarity. The numbers match, the geometry rhymes. It leads to a question that sounds like madness until you look at the math. Is it possible that the Big Bang was not a beginning in the way we think? Is it possible that our entire universe is simply the interior of a supermassive black hole in another, larger cosmos? To understand this, we must look at density. We usually think of black holes as incredibly dense objects, stars crushed down to the size of cities. And for small black holes, this is true. But the math of the Schwarzschild radius has a strange property. As the mass of a black hole increases, its average density decreases. If you double the mass of a black hole, its radius doubles, but its volume increases by a factor of 8. This means the stuff inside gets less crowded. A black hole the mass of the Earth would be denser than atomic nuclei. A black hole the mass of the Sun would be as dense as a mountain. But if you keep going, if you build a black hole the mass of 1 billion suns, the average density drops to that of water. You could swim inside it. And if you go even further to the scale of the truly gargantuan, the density drops to that of thin air. Now, take this logic to its limit. Calculate the Schwarzschild radius for the total mass of the observable universe. All the stars, galaxies, gas, and dark matter we can see. If you plug that colossal number into Einstein's equation, you get a radius of about 13.8 billion light-years. This number should send a shiver down your spine. It is almost exactly the size of the observable universe. The density of our universe is roughly 9.9 times 10 to the 30 grams per cubic centimeter. That is the exact density required to make a black hole the size of our universe. We are living in a cosmos that fits the precise description of a black hole event horizon from the inside. We are floating in a solution that is exactly the right density to be a trap. This is not a conspiracy theory. It is a coincidence that keeps cosmologists awake at night. If we are inside a black hole, then the Big Bang was not a magical explosion from nothing. It was the moment the star in the parent universe collapsed. In that higher dimension, a massive star ran out of fuel. The gravity won and it imploded. The singularity formed. But as we discussed with the concept of the bounce, instead of crunching down to zero, the space inside twisted and expanded. To the observer outside, in the parent universe, it looked like a black hole forming, a dark sphere of silence. But to us, on the inside, it looked like an explosion of space and time, the birth of a world. We are the aftermath of a collapse. We are the dream of a dying star. This theory, known as black hole cosmology, solves many of the headaches of modern physics. It explains why the universe seems to be fine-tuned for life. If universes are born from black holes, then there is a kind of cosmic evolution, a natural selection of worlds. Universes that produce many black holes will have many children. Universes that cannot produce black holes, because their laws of physics are too weak or too chaotic, will be barren. They will have no offspring. Over eternity, the multiverse fills up with universes that are optimized to create black holes. And what does a universe need to create black holes? It needs stars. It needs gravity. It needs complex chemistry. It needs carbon, oxygen, and iron. In short, it needs the exact same conditions required to create life. We are not a lucky accident. We are a side effect of the universe's reproductive system. We exist because our universe is fertile. Pause and let that sink in. You are sitting in a room, on a planet, orbiting a star inside a galaxy. But that galaxy might be drifting inside a bubble of space-time that is effectively the interior of a titan. We are the stuff that fell in. The atoms in your body might be the recycled matter of a 4D sun that perished eons ago in a realm we can never see. It changes the feeling of the night sky. The darkness is not an empty void. It is the walls of the womb. We are safe inside the event horizon, protected from the rest of the multiverse by a barrier of light and causality. The expansion of our universe, the fact that galaxies are rushing away from each other, might simply be the result of falling. In the interior of a black hole, all paths lead to the future. The expansion of space is just the geometry of our descent. But if we are in a black hole, where is the singularity? Where is the drain? In our universe, we see the expansion accelerating. Dark energy is pushing things apart. This doesn't look like falling toward a center. It looks like flying apart. This is where the analogy gets complex. Some physicists suggest that the singularity is not a point in space ahead of us, but a point in time behind us. The Big Bang itself was the singularity. We are moving away from it. In this inverted geometry, the white hole model works best. We are inside the white hole phase of the collapse, the rebound. We are riding the explosion outward. Eventually, perhaps the energy will dissipate and the universe will recede again, or perhaps it will expand forever, approaching the event horizon from the inside, never quite reaching it, frozen in an eternal asymptotic drift. This perspective offers a strange comfort regarding the limits of knowledge. We often wonder what lies outside the universe. If we are in a black hole, the answer is simple: another universe. A universe with different stars, different laws, maybe even different dimensions. And inside that universe, there might be other black holes containing other universes. It is a fractal structure, a nesting doll of realities, worlds within worlds, stretching down to the microscopic and up to the infinite. Our massive black holes, Sagittarius A, M87, might contain baby universes of their own deep inside their event horizons. When we look at that picture of the black hole, the ring of fire and the dark shadow, we might be looking at the exterior of a nursery. We might be looking at the skin of a new reality. This idea connects the very large to the very small in a way that feels almost spiritual, though it is grounded in the hard math of relativity. It suggests that size is relative. To a creature in the parent universe, our entire cosmos is just a small, dark sphere, a heavy dot in their sky. To us, it is vast and endless. And to the creatures inside the atomic scale black holes we might be creating in our particle accelerators, their world is as vast as ours. As above, so below. The ancient alchemists had a slogan that now looks like a prediction of holographic cosmology. The pattern repeats. The structure holds. There is also a resolution here to the feeling of isolation. We often feel small and insignificant in the cosmos, but if this theory is true, we are intimately connected to a lineage of universes. We are part of a family tree. Our universe inherited its laws, the speed of light, the strength of gravity, the charge of the electron, from its parent. We are carrying the genetic code of the cosmos, and every time a star collapses in our sky, every time a new black hole forms, we are passing that code on. We are playing our part in the survival of existence. We are not just dust in the wind. We are the carriers of the fire. But what does it feel like to live in a black hole? It feels exactly like this. It feels like gravity holding you to the floor. It feels like light traveling at a finite speed. It feels like time moving forward. The conditions we consider normal are the specific conditions of a black hole interior. We have evolved to thrive in a trap, and perhaps trap is the wrong word. A trap implies you want to leave. But where would we go? The parent universe might be a chaotic, deadly place filled with radiation that would vaporize us in an instant. The event horizon is not a prison wall. It is a hull. It is the shell of the egg. It protects the delicate experiment of life from the raw fury of the higher dimensions. We are hidden away for a reason. As we drift through this chapter, the boundaries of self and universe begin to blur. If we are inside a black hole, then we are literally made of the material that was swallowed. We are the transfigured ghosts of the past. The iron in your blood was forged in a star, yes, but that star might have formed from the gas of a collapse that happened before time began for us. We are the memory of the parent universe, given new form. And as we look at the black holes in our own galaxy, we must wonder, are there eyes looking back? Are there civilizations inside those dark spheres, looking at their own microwave background, wondering if they are inside a black hole, never guessing that their outside is our inside? The silence of the black hole becomes a silence of infinite depth. It is not empty silence. It is the silence of a library filled with unread books. Every black hole is a potential library of universes. The darkness is teeming with potential. It is the most fertile substance in existence. We used to fear the dark because we thought it was the absence of light. Now we know it is the home of the light. The light we see is just the surface. The dark is the volume. The dark is the bulk, and this brings us to the edge of our understanding. We have asked where black holes come from, what happens when you fall in, how they die, and if we are inside one. We have turned the object inside out. We have dismantled the fear and replaced it with awe. But there is one final step. If the universe is a black hole, and if black holes eventually evaporate or transform, what is the ultimate fate of this system? And more importantly, what is the role of the witness? Why is there someone here to ask these questions? In a universe of blind gravity and dumb atoms, why did a piece of the black hole wake up and start thinking about black holes? This is the mystery of consciousness. Is it possible that the universe is not just a machine, but a mind? Is the complex network of galaxies connected by filaments of dark matter and threads of gravity, similar to the network of neurons in a brain? If we are inside a black hole, are we inside a thought? The final leg of our journey will not be through space or time, but through meaning. We will ask if the black hole is the universe remembering itself. We will close the circle. The stars above you are steady. The ground is firm. But you know the truth now. You are floating in a bubble of curved space-time, drifting in a river that flows toward tomorrow, held in the embrace of a geometry so vast it looks like freedom. You are a child of the event horizon, and you are safe here. The monster has already swallowed you, billions of years ago, and you are still alive. You are still dreaming. The digestion of the universe is a slow, gentle process called life. Take a breath. Feel the air filling your lungs. That air is held by gravity. That gravity is the curve of the black hole. You are breathing the physics of the interior. You are perfectly adapted to the dark. And as we prepare for the final drift, the last chapter of our long night, we let go of the need to escape. We accept our place. We are the explorers of the inside. We are the lanterns lighting up the belly of the whale. And we have one last light to shine. Chapter 10 awaits the end of the journey, the moment where the observer and the observed become one. Are we the universe remembering its own motion? Are we the ghosts of the light that fell in? The answer is waiting in the final silence. We have reached the end of the fall. We have drifted through the silence of the event horizon, survived the crushing tides of the interior, and touch the impossible point of the singularity. We have watched the black holes evaporate into the cold future and wondered if we are living inside one right now. But there is one final question that haunts this journey, a question not about gravity or time, but about us, about the witness. Why is there a mind here to perceive the dark? In a universe made of dead rock, burning gas, and invisible vacuums, why did a portion of the matter wake up? When you look at the image of a black hole, that glowing orange ring surrounding the shadow, something profound is happening. Photons of light, which have travelled for 55 million years from the heart of galaxy M87, are entering your eye. They are striking your retina, turning into electrical signals and racing into your brain. There, a collection of atoms, carbon, hydrogen, oxygen, nitrogen, is interpreting that signal. The universe is looking at itself. The black hole is being seen by the dust it created. This loop of observation is the deepest mystery in physics. Quantum mechanics tells us that the observer is not separate from the experiment. The act of measuring a particle changes its state. Until you look, the electron is a wave of probability existing everywhere at once. When you look, it collapses into a point. It becomes real. This suggests that reality requires a witness. Without us, or something like us, does the universe truly exist? Or is it just a ghost of potential? The black hole challenges this idea because it is the ultimate unobservable. It hides its secrets behind a wall of causality. But as we learned with the holographic principle, the information of everything that falls in might be stored on the surface. The event horizon might be the most complex hard drive in the cosmos, recording the history of every atom, every star, and perhaps every civilization that has ever touched the void. If the universe preserves information, then memory is not just a biological trick of the human brain. Memory is a fundamental law of physics. It is the conservation of data. When you remember a childhood moment, the smell of rain, the voice of a friend, you are replaying a pattern of neural firing. That pattern is energy, and energy cannot be destroyed. It can only change form. In a strange way, your memories are just as physical as the stars. They are imprinted on the space-time of your brain, and by extension, on the universe itself. The black hole is the grand archivist. It collects the scattered pages of cosmic history, the light we lost, the matter we forgot, and binds them together in the dark. It ensures that nothing is ever truly erased. This leads to a poetic yet scientifically grounded possibility, that we are the universe's way of remembering its own motion. We are the temporary vessels for information. For a brief flicker of time, 70, 80, 90 years, we hold a complex pattern of energy together. We take in sunlight, we take in food, and we convert it into thoughts, into art, into love, into questions. We fight against entropy. The black hole represents the ultimate entropy, the final resting place of order. But we are the resistance. Life is the universe's refusal to go quietly into the dark. We are the white caps on the waves of the black ocean. Think about the atoms in your right hand. They were forged in the heart of a dying star that exploded billions of years ago. That explosion scattered the iron and carbon across the galaxy until gravity pulled it together to form the Earth, and eventually, you. But where did that star come from? It came from the primordial hydrogen of the Big Bang. And where did that hydrogen come from? Perhaps, as we discussed, from the white hole of a parent universe. You are a direct descendant of the singularity. You are not in the universe. You are the universe. You are a piece of the black hole that has cooled down enough to think. You are gravity that has learned to love. There is a deep peace in this realization. It dissolves the loneliness. We often feel small when we look at the night sky. We feel like insignificant specks on a lonely rock. But physics tells a different story. It tells us that we are necessary. We are the way the cosmos knows itself. As the great Carl Sagan said, we are made of star stuff. But we can go further. We are made of the same geometry that curves the black hole. The gravity that holds you to your chair is the same force that crushes the star. The light that allows you to read these words is the same cousin to the Hawking radiation that evaporates the monster. It is all one fabric. There is no out there. There is only here. And what happens when we die, when our biological pattern dissolves? The atoms do not vanish. The energy does not disappear. The information of who you were, the quantum state of every particle that made up your life, returns to the chaotic flow of the universe. It might be scattered into the soil, lifted into the air, or radiated out into space. Eventually, eons from now, it might fall into a black hole. And there, on the event horizon, you will be archived. You will become a hologram on the edge of eternity, preserved in the geometry of the final night. We are destined to become part of the black hole's memory. We are returning to the source. As we end this journey, look around the room you are in. It seems solid. It seems mundane. But it is a miracle of stability. You are living in the Goldilocks zone of space-time, not too dense, not too empty, not too hot, not too cold. You are living in the brief, beautiful era of the stelliferous universe, the time of light. The black holes are waiting in the dark, patient and eternal. They are the bookends of time. But in the space between them, we have this moment. We have the chance to wonder. We have the chance to explore the edge of the abyss and find beauty there. The black hole is not a place where physics dies. It is a place where physics reveals its deepest truth, that everything is connected. The singularity connects the beginning to the end. The wormhole connects the here to the there. The hologram connects the inside to the outside. And the observer connects the matter to the meaning. You are the bridge. You are the event horizon where the universe meets itself. So tonight, when you close your eyes, do not fear the dark. The darkness inside your mind is the same as the darkness between the stars. It is a space of potential. It is a canvas waiting for a dream. Let yourself drift in that vast, quiet interior. You are safe. You are held. You are drifting in the gentle gravity of a universe that wanted you to exist. The journey to the black hole was never about leaving home. It was about understanding where home really is. We are the children of the dark, carrying the fire of the stars in our minds. And as long as we keep asking questions, as long as we keep looking up, the light will never truly go out. If this journey into the deep has brought you a moment of awe or a quiet sense of connection to the vastness, I am deeply grateful you walked this path with me. A gentle like or a soft tap on subscribe helps this signal travel further through the algorithm, reaching other wandering minds who might need a moment of cosmic peace. It is a small gesture, but like a particle dropping into a black hole, it adds to the mass of this community, keeping our gravity strong. And please tell me in the comments, if you could jump into a black hole and emerge anywhere or anywhen, where would you go? Would you see the beginning of time or the end? I read every story you leave, and they remind me that we are not drifting alone. Until next time, Keep looking up. The universe is turning softly around you. The mystery is not out there, it is right here, beating in your chest.